Hi, in this session we're going to talk about free body diagrams. A free body diagram is a diagram that shows all the forces acting on an object in a particular situation. So we have two goals for this particular session. First, we're just going to cover some details about how you draw free body diagrams. Secondly, we will see how free body diagrams can help us when we apply Newton's second law. So just to cover why we do it, we draw free body diagrams to help us understand why something moves the way it does, or if it's not moving, why it remains at rest. So if we want to understand this, it is very helpful to draw a free body diagram. And again, a free body diagram shows the various forces that act on an object. And it also gets used as just kind of a pictorial method of keeping track of all the forces. Now, Newton's second law says add up all the forces as vectors. So usually we draw a free body diagram first. That shows us all the forces. And then we can look at it when we apply Newton's second law. Remember, when we're applying Newton's second law, we're adding the forces as vectors. So it's very important to note which way the force goes, and that is shown on the free body diagram. There are really two rules of thumb to keep in mind when you draw a free body diagram. First of all, think about what applies each of the forces you drew. If you're drawing a free body diagram, you put a force on the diagram, and you can't identify what other object applies that force to the object you're drawing the free body diagram of, then you're in trouble. Maybe there is no such force. Also, when you're finished drawing your free body diagram, think about what the net force is. If you sort of add up all the vectors in your head that you've drawn, do you get a net force or not? And is the net force, as shown by the free body diagram, consistent with the object's motion according to Newton's laws? Remember that Newton's law, and this is really Newton's second law, sum of all the forces equals mass times acceleration. Okay, so we'll do an example. So here we have one box, box 1, small, sitting on top of a larger box, box 2. You're actually picking these boxes up, supporting them at the bottom of box 2, and you're holding them at rest initially. Okay? So what we're going to do is, remember, this is the situation we have, box 1 on top of box 2, and in fact, you are not shown, but you are holding these boxes at rest by simply putting your hands underneath box 2. So let's consider which forces act on box 1 in this situation. Okay, so let's go over some possibilities. Do we have, for instance, a force of gravity acting on box 1? Do we have a normal force applied by box 2 on box 1? Do we have a normal force applied by you on box number 1? There's some options. Well, yes, we certainly do have a gravitational force. So this, remember, forces are, when we talk about forces, we talk about interactions between things. So here we have an interaction between the Earth and box 1. You know, you're going to pick these boxes up, you're in your room, you're moving into your apartment, or whatever. You're on the Earth when you're doing this, so the Earth is involved here, and the Earth definitely exerts a downward gravitational force on box 1. There is certainly also an upward normal force applied by box 2 on box number 1. You always get a normal force when you have contact between objects. So box 1 is clearly in contact with box 2. The Earth is trying to pull box 1 down. 2 is preventing box 1 from falling down by applying this upward normal force. On the other hand, there is no upward normal force applied by you on box number 1 because you are not directly touching box 1. Your hands are underneath box number 2, so you cannot exert directly a force on 1. Now, some of the force that you apply to 2 is then kind of passed on by 2 to box 1, and that's this normal force applied by 2 on 1. Okay, so we have a relatively simple free body diagram. It's very similar to what we get if we just had box 1 sitting on a table. We have an upward normal force exactly balancing the downward force of gravity. Okay, so if you look at this, the net force on here is 0. That's consistent with the box remaining at rest. Also, we can identify the two objects that are acting on box number 1. The Earth applies the downward force of gravity. Box 2 applies the upward normal force. Okay, same situation, but now we're going to draw the free body diagram of box number 2. Which forces act on 2? So let's go over again some possibilities. Downward gravitational force, upward normal force applied by U on 2, downward normal force applied by 1 on 2, or would it be equivalent to say, instead of a downward normal force, just a downward force of gravity? So let's go over those in turn. So yeah, we certainly have a downward gravitational force applied on box 2 by the Earth. So this is this downward M2G force. Your hands are underneath the box. You're providing the support upward, preventing these boxes from moving down. The Earth is trying to pull them down through the force of gravity. So there's your upward normal force. And yes, there's a downward normal force applied by 1 on 2. And you actually want to show it like this, as a downward normal force applied by 1 on 2. You do not want to do that. There are two good reasons why you don't want to show a downward M1G force acting on 2. The first reason is that M1G is a force of gravity, and it's clearly associated with box 1 because there's an M1 right in the equation there. Okay, so when you're drawing a free body diagram of an object, in this case we're drawing the free body diagram of box 2. If you're drawing the free body diagram of that object, you only include forces that are directly applied to it. M1G is a gravitational force applied to box 1. It doesn't show up on box 2's free body diagram, but belongs on box 1's free body diagram. That's where we put it already. Now you could argue with me that I'm being pretty compulsive here, and that we're going to find out that the downward normal force applied by 1 on 2 is equal in size to M1G. So why can't we just do these things interchangeably? Well, in this case, it's true that Fn 1 on 2 is equal to M1G. However, in another case we're going to see in a few minutes, they're not going to be the same. Okay, so they are not interchangeable in all cases. So you better get into a habit of just putting the right force down right off the bat. Fn 1 on 2 is associated with the interaction between box 1 and box 2. So if you look at it overall, we've got the three interactions that box 2 is involved with. First with the Earth, then with you, then with box 1. So here's our overall free body diagram. Turns out that, again, the total upward force applied by you on box 2 balances the total of the two downward forces acting on 2. So the net force on 2 is 0. All the forces cancel out. That's consistent with box 2 remaining at rest. And we can also identify all the things that box 2 is interacting with, and we've got one force for each of those interactions. Okay, another thing we could do is, instead of separating out box 1 and box 2, we could kind of treat them as one system and draw a free body diagram of the whole two-box system. So let's see which forces we would get on our free body diagram. Because sometimes this can be an easier free body diagram, and so you can actually do some calculations more easily with this free body diagram than with the free body diagrams of the separate boxes. So what we have here is basically just one combined object with a total mass of m1 plus m2. That's interacting with the Earth, so we certainly have a downward force of gravity, m1 plus m2, all in brackets, times g. That's that downward force of gravity. That's the interaction of our system with the Earth. This system is also interacting with you. You're supporting this system. So there's an upward normal force applied by you on box 2, but that's also applied. Box 2 is part of the system, so this is you on the system too. Same thing. And that's it. So those two upward forces, those two forces are equal and opposite, and they cancel out. And so the net force is 0, and we've got two interactions, one with you and one with the Earth, that we were accounting for in this free body diagram. Okay, so that's the basics of how you draw a free body diagram. Now, why did we bother drawing the free body diagrams? So, well, this is why. We're going to now calculate some things. Okay, so let's see. Oh, before we get there, sorry. We're going to go back and see that the free body diagram of the system can be seen as just the sum of the free body diagram of box 1 added to the free body diagram of box 2. Okay, so you combine those two free body diagrams, you should get this free body diagram of the system. Okay, so let's see what we got here. So the free body diagram of the system has a normal force applied by U on box 2. Well, there it is right there on box 2's free body diagram. The overall system has an M1 plus M2G. Well, that's the combination of the two individual gravitational forces acting on box 1 and box 2. M1G and M2G, add them together. When you put the free body diagrams together, you get M1 plus M2, all multiplied by G. Okay, so looks good. Well, wait, we've got an extra force, Fn2 on 1, and another one, Fn1 on 2, that we don't see on the system's free body diagram. Well, what's up with that? Well, this is where Newton's third law comes in. Newton's third law says that if box 2 applies a force to box 1, then box 1 applies an equal and opposite force to box 2. So those two forces, we showed them in opposite directions, but they're also equal in magnitude. Okay, so when we put these two diagrams together, those two forces just simply cancel out. They're equal and opposite. So that's why we don't see them showing up on the system's free body diagram. For the system's free body diagram, those are known as internal forces. The system is box 1 and box 2 together, so we don't need to worry about interactions between the boxes on that free body diagram. And as we see, those interactions will cancel out. Okay, on to do some calculations. This is where we bring in Newton's second law. So we go back to box 1's free body diagram. Two forces, they're equal and opposite. So what is the normal force applied by box 2 on box 1? Okay, so here we go. We write down Newton's second law. Sum of all the forces added up as vectors on box 1 is the mass of box 1 times box 1's acceleration. So that's just Newton's second law. Then, to help us evaluate the left-hand side of this equation, sum of all the forces added as vectors, that's why we drew the free body diagram. Because now we can figure out what all the forces are acting on one and then just add them up as vectors. So here we've just got one dimension to worry about. The forces are vertical. All forces are vertical in all three free body diagrams we drew. So we define a positive direction. In this case, I'm just going to define up to be positive. So all forces up are positive, all forces down are negative. So this is where the signs come from in the equation. Okay, so we're evaluating the left-hand side by looking at the free body diagram. We have two forces. The normal force applied by 2 on 1 is up, so that's in the positive direction. Then we have M1G. That goes in with a minus sign because it's in the downward direction. We chose up to be positive. Okay, so that's how we use the free body diagram to evaluate the left-hand side. Sum of all the forces added up as vectors, that side of the equation. On the right-hand side now, we're evaluating M1 times A. Well, what's the acceleration in this case? Well, these guys are at rest. This box is at rest in this particular case, so there is no acceleration. So that's where the 0 comes from the fact that the acceleration is 0. Okay, so that allows us to show that the normal force applied by box 2 on box 1 is, in this particular case, equal to the force of gravity applied by the Earth, equal in magnitude to the force of gravity applied by the Earth on box 1. Those forces are in opposite directions, but here we're just getting the magnitudes. So we're showing that the magnitudes are equal. Okay, so let's try the same thing with box 2. A little more complicated because we have a third force. Okay, but the process is very, very similar. So first we write down Newton's second law for box number 2. So that means we're adding up all the forces as vectors on box 2. And Newton's second law says the sum of all the forces added up as vectors on box 2 is box 2's mass times its acceleration. Again, we choose a positive direction. Let's make up positive again. That sets the signs for our different terms. Anything going up is positive. That's only the force, the normal force exerted by U on box 2. Anything going down, the normal force applied by box 1 on box 2, is a downward force. That goes in with a minus sign in our equation. M2G, that's directed down. That's the force the Earth exerts on box 2. That goes in with a minus sign as well. So, with the help of our free body diagram, we evaluate the left-hand side of Newton's second law. Then we set it equal to m2 times box 2's acceleration, but in this case box 2's acceleration is 0, so once again we get a 0 on the right-hand side. Okay, so let's solve for the normal force applied by U on box 2. So we just rearrange the equation. We get Fn, normal force, applied by U on 2 is Fn, normal force applied by 1 on 2, plus m2g. Now, when we did the free body diagram of box 1, we just figured out the normal force applied by 1 on 2 in this case has a value of m1g. So we can replace Fn 1 on 2 by m1g. So when we're done, we get the normal force applied by U on box 2 is m1g plus m2g. Okay, so let's do that again. We're going to do the same calculation and try and find the same thing, but with our system free body diagram. So we go back to our system free body diagram. So we've got the two forces that are equal and opposite, that are equal in magnitude and opposite in direction. Okay, that's what we mean by equal and opposite. And we apply Newton's second law to the system. Sum of all the forces added up as vectors on the system is the system's mass times the acceleration of the system. Pick a positive direction. Let's go with up again. That worked before. Okay, so now we solve for the normal force applied by U on 2. That's equal to, so here we get the signs. Positive for the normal force, negative for the gravitational force. Set it equal to 0 because the acceleration of the system is 0. So the normal force applied by U on 2 is exactly the same as what we calculated when we did the free body diagram of box 2. It's m1 plus m2g. Well, that's good. It should be the same. We should get the same answer no matter how we do it. So that's good. Okay. Now we're going to change the situation. So now you're picking these boxes up and giving them an upward acceleration. So what do we change on our free body diagram? Well, it turns out that, well, we're stuck with the gravitational force. We can't change that. But we need a net force directed up. Where it comes from is the fact that the normal force applied by 2 on 1 increases in size. Okay. We're going to apply Newton's second law again. We just write it out. Pick a positive direction. Up is positive. That's really because the acceleration is directed up in this case. Okay. That sets the signs. Fn 2 on 1 is positive, it's up. M1g, negative, it's down. In this case, we don't set it equal to 0, okay, because there is a non-zero acceleration here. So in this case, the normal force applied by 2 on 1 is not m1g anymore. Okay, it's m1 times g plus a. So this goes back to near the beginning when I said you don't want to say that Fn of 2 on 1 is always equal to m1g. It's not. Here's a case where it is not. Okay, keep going. We'll do it for box 2. Once again, we're stuck with the force of gravity. That doesn't change. Doesn't care. The Earth doesn't care which way the box is accelerating. Still has the same force on box 2. But the two normal forces both increase in size. We'll apply Newton's second law to box 2. So we just write out Newton's second law, pick positive direction. Hey, let's go with up. That sets the signs on our terms in our force equation on the left-hand side. Anything up is positive. That's the normal force exerted by U on 2. Anything down is negative, the other two forces. We set them equal to mass of the of the system we're drawing the free body diagram of, that's box 2, times the acceleration. Okay, so let's go solve for the normal force you apply on box 2. Okay, so you rearrange the equation, you get the normal force applied by 1 on 2 plus m2g plus m2a. Now remember, normal force applied by 2 on 1 we just solved as m1g plus a, so we're going to put that, oops, sorry. We're going to put that in there we go. And when we're done, we're going to get, you can see on the right hand side, m1g plus a plus m2g plus a. We should get the same result coming out of here. Okay, free body diagram of the system. That force, normal force applied by U12, is bigger than it was before when the boxes were at rest. Write out Newton's second law. Pick a positive direction. That sets the signs on the left-hand side of our equation. Solve for the normal force applied by U12. Voila! We get the same answer we got before from the free body diagram of box 2. Okay, great. Free body diagrams.